All right, good morning, ladies and gentlemen. Section 2.4, rates of change, slope, and tangent lines, which are all applications of limits. If it bothers you that that stupid pen stays on the board, it's driving me batty and I don't know how to get the dang thing off of there. However, technology sucks. Okay, so make sure you have your calculator here. In a little bit, we're not going to do this right away, but I want to go over a couple different ways to be pulling some numbers out of your calculator if you forgot. But basically what we're going to do is we're going to look at this example, f of x equals x squared minus 4, okay? And we're going to find the average rate of change over the interval of x between 1 to 4. Now what that actually means is basically find the rate of change from x equals 1 to x equals 4, okay? So we're finding the rate of change from x equals 1 to x equals 4, okay? Before we do that, okay, average rate of change. This is a very common problem that comes up a lot in calculus. They talk about average rate of change a lot. So these are all, if you're wondering, why do we keep coming back to this average rate of change? It's because it's a very important topic, okay? So let's take a little gander here. What does this problem look like graphically? I'm just going to take that screen off, and I already made the sketch because I didn't want to waste time making a sketch. And basically, what this is asking me is it's saying, you know, find the average rate of change from this point all the way up to this point, okay? From point to point, what's the average rate of change? Now, if you think about this, think about it like, well, you found average rate of change of lines because lines are constant. Their rate is the same everywhere, so their average between any two values, okay, is the same. But when we start looking at parabolas and cubics and non-linear graphs, okay, what we need to understand is the rate of change, okay, graphs, curves have slope, okay, and their slope changes at every point. If the function's increasing, the slope is increasing. If the function's decreasing, the slope is decreasing. Okay, so there's a whole bunch of different slopes on this graph. So if I'm finding the average rate of change between 1 to 4, what I'm doing is I'm coming along and I'm finding all of these slopes, this infinite number of slopes, all the way up on that graph, beginning at x equals 1 to x equals 4. What I'm trying to do is I am trying to add up the infinite, yes, I said infinite number of slopes between x equals 1 and x equals 4, which basically is kind of impossible, isn't it? There's an infinite number of slopes between 1 to 4 because we can keep adding decimals, okay? Well, it seems really wonky and crazy, but there's actually a very easy calculation to do this, and we've already done it, okay? We have found numerous times in Algebra 2, you found some in pre-calc, we've done them this year already. We have already found the average rate of change, the AROC, average rate of change, okay? Anytime you see that, on any interval from A to B, okay, and we found that by saying f of b minus f of a over b minus a. And it's important to see because this interval right here, that interval is always an interval in terms of x, all right? So we're finding all of these points, and basically what it is, okay, it's simply just the slope between these 2 points, all right? So if I came in here and I found the average rate of change from x equals 1 to x equals 4, what I'm doing is I'm taking my ordered pair, this one and this one, and I'm just finding the slope between them. So I'm really just taking 12 minus -3 over 4 minus 1. Well, that gives me 15 over 3. So my average rate of change is 5, okay? Now, please understand, 99.9% of the time, there are units on that. What's the average rate of change? 5. Well, 5 what? but we don't have any units on this particular problem, so we're just going to leave the units naked. Typically, it's a rate of change. It's your y-axis divided by your x-axis, however they would be labeled, feet per minute, feet per second, anything like that. That's our average rate of change, okay? So bottom line, the average rate of change from 1 to 3, the average rate of change is going to be 5, and it is simply the slope between 2 points. That's all my average rate of change is a slope between 2 points. Now, in this case, it's between 1, 3, negative 3, and 4, 12, okay? There's my interval, 1 to 4. It's simply the slope between those 2 points. But it's actually another thing, okay? It could actually be looked at in another way. If I look at these 2 points, okay, what I'm actually doing is if I look at these 2 points, if it's a slope between those 2 points, it is also, I want this to be red now, okay, it's also that guy right there, okay? It's also can be known as the slope of the secant line. It is also slope of the secant line from x equals 1 to x equals 4, okay? So I can think of it as the slope of the secant line, the slope between 2 points. Essentially what I did, in a way, is it's kind of, although it's impossible to sum up all those infinite slopes between there and divide by infinity, okay? But if I find the slope between these 2 points, that's going to give me my average rate of change. Now, this is going to blossom into something later on called the mean value theorem. And what the mean value theorem states is if I find, basically, I'm going to summarize it, if I find the slope on a curve between these 2 points, between any 2 points, and that function is continuous and differentiable on that interval, that somewhere between the open interval from 1 to 4, there exists some point in there that is going to have a slope of 5 in this case, somewhere in there, okay? And people are probably looking cross-eyed saying, what the heck does that mean? Well, it's kind of like Grandma's theorem. If you're driving 65 miles an hour on your way to Grandma's, because we know everybody speeds, let me rephrase that. If your average speed on the way to Grandma's house is 65 miles per hour, somewhere, somehow, as you were on the way to her house, you were going 65 miles an hour. Sometimes you were going slower, sometimes you were going faster, but at one point, you were going 65, okay? So we're going to take this to the next one. And we're going to do an example here, and it says, find the slope of f of x at the point 1, 3, okay? So what this is asking for is this is looking for the slope of f of x at x equals 1. We want to find the slope specifically at the point I have labeled on my graph, okay? And you can graph that, sketch that graph in there by hand if you wish. But there's actually 2 ways to do this. And you've actually done this both ways, okay? There's 2 ways to do this. The first way we can do it is we can estimate the slope at 1, okay? But we understand, we know that this is a very confident estimate that we're doing, okay? And what do you mean? Well, we're going to find close points. I'm going green. We're going to take close points. What do you mean close points? Well, if I picked a point on the right side of 1 here, okay, let's say if it would draw in there, let's say I'm at 1.001 comma, don't really know. My calculator is going to do the math for that. Okay, so I could pick that point. Or I didn't have to pick on that side. I could have also picked on the other side. I could have picked really close on this other side here, but that would have been like 0.999 comma, let my calculator find it. Okay, I could find the slope between my green point and the black one or the purple one and the black one. And although it's going to be an estimate, we are confident in that estimate. Okay, we know what it's going to be. So basically, we're looking for the AROC between 1 and maybe 1.001, or depending how you did it, we could say 0.999 and 1. Okay, we're going to take that really close. And from here is where I want you to take your calculator. And in the calculator, we'll be doing this a lot this year, okay, if you don't have yours, make sure you open up a calculator page. And what we're going to do is we are going to define our function on the calculator, meaning once you got your calculator page open, let me stretch this little bugger. My calculator's messed up on my screen. Let me get him in there so I can see it all. Okay, so I'm in a calculator page, so I'm going to say menu, actions, define, which is menu 11. And we're going to define that function however we want, except I'm going to call it f of x, and I'm going to say that equals x squared minus 4. And it's going to say bada bing, bada boom, there it's done. It is defined. And then what I'm going to do is I'm going to look at it in my AROC here, okay, so what do you mean, Kruger? What do you mean we're going to look at it in our AROC? So basically, I'm going to plug this in, and I'm going to be looking for my AROC. So I'm going to be taking f of 1.001 minus f of 1 over 1.001 minus 1. And I don't want to do these calculations on my own, so that's why I said I'm going to let my calculator do it. So, oh, what did I just do there? Didn't want to do that. That's not the one I want. Oh yeah, that is the one I wanted. So from here, I'm going to come down, I'm going to grab my calculator back, and I'm going to do my old control divide trick here. And because my function's defined as f of x, I'm going to say f of 1.001 minus, in function form, f of 1, f of 1, and then I'm going to say 1.001 minus 1. Now it doesn't matter which way you are. And it looks like, I don't know, if I was making an estimate on that, I would probably call it 2, just because it looks like it's 2. And if you're not confident in that, just remember, we can come up here and we can add another 0 in here. Oh my, it's going slow on me. I can come in here and I can add a 0 in the top, and I can add a 0 in the bottom, but it's not working for me. 0, 0, everything's crashing on me. I'm back, it wasn't crashing on me, I forgot to copy it down. But if I add a 0 top and bottom to make that interval smaller and smaller, I can see I'm getting closer and closer to 2. So, boy, by golly, it certainly seems to me that the slope, okay, that my slope at, come on, get my pen, really means my slope at the point 1, -3 is 2. Sure looks like my slope is going to be 2 right at that point, approximately. Again, it's a confident estimate. We can see the closer to 1 we get, the closer to 2 it's getting. So we can make that, okay? The second way is the exact way, which technically involves a rigorous math test. Oh boy, everybody's saying a rigorous math test. Well, that rigorous math test we've been learning, it's called a limit. And what we are going to do is that rigorous math test is also called a limit with the difference quotient, which you would have done many of those last year in pre-calc. But, of course, because we were all quarantined or school was out, we couldn't do that. So what we're going to do the exact way, okay, is we're going to take an interval from 1 to 1 plus h. And then we're going to let h slowly approach 0. We're going to limit the distance in h as it goes to 0. So the way we're going to do this is we're going to say the limit as h approaches 0 of, remember, our function f of x actually equaled x squared minus 4. So we're finding the AROC, okay, from 1 to 1 plus h. There's my A, there's my B. So in order to plug that into my AROC, I am finding f of 1 plus h minus f of 1 all over 1 plus h minus 1. Now, if you would have done this numerous times last year, you would have instantly identified, no matter what number my interval is here, if it's 2 or it's 3, whenever I add h to it, hopefully you're catching, that's going to go away. And what happens is we always end up having the limit as h approaches 0 of f of 1 plus h minus f of 1 in this case over h. Okay? And then from there is where we need to start doing our math, because this right here in this step, I'm written in function form. So what I need to do is I need to see the limit as h approaches 0. And when I taught pre-calculus and calculus, when I used to do this, I always had my students start out making 2 big old brackets here, and I'm over h every time. What is f of 1 plus h? Well, that just says plug 1 plus h in for x everywhere I see an x. So I get 1 plus h, I got to square that, minus 4, and then that's minus f of 1, that's saying 1 squared minus 4, okay? And then what I need to do is I need to just multiply things out. Now, you're going to see me many times here. I know how to expand this really quick. It's 1 plus 2h plus h squared. And if you don't remember that, let me show you your pattern of an a plus b. If I'm squaring any binomial squared, it's always going to be the first term squared plus 2 times the first term times the second term plus the second term squared. And I can expand that really quick without doing my double distribute. And I also have a difference. A difference of squares, okay? Now this isn't factoring, this is expanding. Again, it's the same thing, it's the first term squared, but this time because of that minus, it's minus 2 times the first term times the second term plus the last term squared, because I'm always going to take a negative times a negative, okay? So I'm always going to expand that out, and I'll always do a lot of my math on top of my parentheses there so that I can look at the limit as h approaches 0 of, and I can see I can put my 1 and my minus 4 together, so I really have negative 3 plus 2h plus h squared. And then in here I got 1 minus 4, and here I have negative 3, but it's the opposite of negative 3, so I'm going to say plus 3 over h, and then I can kind of see, okay, it's always going to be a test. Everything that's inside that parenthesis needs to reduce out, or another way to say this is, as you're going through this limit process, the only terms in the numerator that are allowed to be left have to have an h in them. Because right now, if I substitute my limit, I get 0 over 0 yet. So I'm going to say my limit as h approaches 0, and I'm going to factor an h out. And then I have 2 plus h. and that's divided by h. And what I've just done there is I've just reduced out my 0 over 0. So now I can apply my limit in here. And as h goes to 0, I can see my slope is 2 at that point. Okay? So what this means is the slope of f of x at x equals 1 is 2. Okay? So what I did is I two ways I can find that slope at a point. Okay, the exact way. This is right here. This is the calculus way. Okay, we can also estimate, but we're not going to do a lot of estimating this year, only because you guys don't have your practice as well as you would have had in for the exact way. So we're not going to do tons of them. However, what we need to do is we need to find that. Now, as I came down here, okay, this is a really cool thing, and I'm going to rewrite this quick. So as I came through, as I went through here, I have the limit as h approaches 0 of 2 plus h. What does it equal? Okay, so this is as h goes to 0. But what this is right here, this expression, 2 plus h, gives me any distance at x equals 1. For instance, in the first page, we found out, we looked for the slope between the points from 1 to 4, where x equals 1 to x equals 4. Well, this h value is the number of units away I am from 1. So if I'm going from x equals 1 to x equals 4, okay, h in this case would have to equal 3. And what is 2 plus 3? It's 5. It's giving me my average rate of change at the same time. And the smaller h gets, okay, the smaller h gets, the closer and closer I get to that point, okay? So the smaller that distance between h gets, before I was way up here, the smaller it gets, the closer and closer I get to the exact slope at 1, okay? So we're going to look here, the exact method. The exact method is called, it's a limit with the difference quotient, okay? To find the slope of a tangent line of a curve at x equals 1, we used an interval of 1 comma 1 plus h, and then we let h equal to 0. Now let me qualify. If I was looking for the slope of a curve at x equals 3, my interval is going to be 3 comma 3 plus h, okay? So this value right here is my interval, and then I'm adding a small change to it, and then we're letting, or I guess it doesn't have to be small, that change can be anything, but by the time we get to the end, we're going to let that change slowly approach 0 for the limit process, okay? So no matter what, if we want x equals 5, then I'm 5 to 5 plus h, okay? And like I said, as you do a few of these, you're going to figure out no matter what that x value is that's plugging in, this guy and this guy is always going to go away, and it's always going to revert to the limit as h approaches 0 of your f of 1 plus h or 3 plus h minus f of whatever I'm looking at. Bottom line, it's going to be over just 1h, okay? So that's one good thing to be able to see there. Now, next page, if I can get to the next page. So the slope of a curve, the slope of curve f of x at point x equals a is given to you right here, where a is any number. Notice the a is anything in here. So as I said, no matter what x is, hopefully you're going to see that that's going to go around, and it's going to quickly go to the limit as h approaches 0 of f of a plus h minus f of a all over h. And then what we need to do is we need to plug in and expand, okay? Now, this is the exact way to find the slope. Exact slope. It is not an estimate. It is perfectly exactly what it's going to be at that particular A value, okay? So, what this means is, okay, right here, when I do this whole slope of the curve, the slope, it can also not just be called the slope of the curve. We need to hear the different verbiage that they're going to use in calculus. They might also say, what is the slope of the line tangent to f of x at x equals a? Okay, or they might say, what is the instantaneous rate of change of f of x at x equals a? They might even say, more often than not, they're going to say, what is the derivative of f of x at x equals a? Okay, all three of these all mean same thing. They are all asking you to do the exact same thing. And as I come down here, the derivative, there's a specific notation for the derivative, okay? And calculus notation, how we'll be doing this sooner than later, we're going to be saying, okay, f prime of a. That little prime up here, it's like an apostrophe, but it's not an apostrophe. It's a little tick mark up there. Means derivative. This little guy right here means derivative of f, which is really dragging us into slope or rate of change at a particular value, okay? And as I come down in problem number 2 that we did before, okay, what we would say in calculus is we would say in problem 2, f prime of 1, meaning basically the way I interpret it, the slope at x equals 1 equals 2 for f of x equals x squared minus 4. Okay, it's only for that particular function. If I have a different function, I need to find a new slope. Okay, but this is how we will write it in calculus. All right. So what we're going to do here is we're going to move to this next one, and we're almost done. Well, we got a little bit here for the day, but I'm breaking this into 2. Okay, very common question. This comes up all the time in calculus. Find the equation of the line tangent to a function at a certain point. Now, if you think back to Algebra 1, Algebra 2, geometry, don't really care, pre-calc, in order to write the equation of a line, there are 2 things we have to have. We have to have a point, and we have to have a slope, all right? So, and notice this is the same exact function that we've done all the examples on. So if I had to take it to another place, okay, I could do it one of 2 ways. I could approximate that slope with my calculator, but right now I think it's better if we use the exact value. But the point, well, what is my point? The point would actually be, well, if it's at x equals 1, I need to find out what is f of 1. Well, what is f of 1? It's going to be 1 squared minus 4. So f of 1 equals negative 2. All right, what? I'm on the wrong thing here. F of 1, actually, negative 3. Now, this is a crafty way to say an ordered pair of 1 comma negative 3. There's my point. The other thing we need is we need the slope, okay? Well, my slope in calculus, how we're going to dictate this is we're going to say, well, we found this back in the previous slide, our previous 2 slides, okay? What we did is we found that f prime of 1, and what did f prime of 1 actually equal? It equaled 2. So that tells me the slope is 2 at x equals 1. That's a bad equals. Okay, so remember, there's always 2 ways to get that. One way is the estimate. and that's taking maybe 1 to 1.001, and we're making that interval tighter and tighter, and then we're going to make a very good approximation off of that. Or 2, there is the exact way using a limit. Okay? And that's what we're going to be doing. We're going to be looking at that. So if we're writing the equation of a tangent line, okay, I got a slope and I got a point. Now, back in the day, write it in this way, write it in this form. Well, there's this cool little form called y minus y1. Okay? And I already know I'm going to have people that are going to say, I'm not doing that. I like a different way. I really don't care. If you want it easy, you're going to change your ways. M times x minus x of 1, where my point is x1, y1, and m is slope. Okay? This is called point slope form of a line, okay? And now the beauty of the deal is, okay, all I got to do is plug in. Here's my x1, y1, and my slope. Here's my slope of 2 up here, okay, my slope 2. So I can take those, substitute them into my equation, and say y minus negative 3 equals 2 times x minus 1. And in this class, I can turn and walk away. The AP test, not if, but when you have to write the equation of a tangent line, they don't care what form it's in. They're going to be happy as a clam right here. Some people might say, yeah, I don't like that. I'm going to write it y plus 3 equals 2 x minus 1. They don't care. They'll give you credit for that. Some people are going to say, well, I want to write it as y equals 2 times x minus 1 minus 3, so that way I can enter it in my graph quicker. They don't care. Some people are going to say, oh, I'm going to expand that out, and I'm going to call it, simplify, y equals 2x minus 5. They don't care. Any of those are going to work, but my high recommendation is stop right there, because when you go further, you could make a stupid sign change, a stupid sign drop, and if you do that, well, now the problem's wrong. So what did we actually do by finding this tangent line? This is kind of neat. What we actually did here is, let me pull up my graph, and I do have our function graphed right here. This is our x cubed minus 4, or x squared minus 4. And in this same graph, if I actually graphed my tangent line, which, what was that little rascal? It was 2x minus 1, parenthesis, minus 3, I believe was it. There's my equation of my tangent line. Okay? Whoa, whoa, don't like that. Go back, get it back where it was. Give me that thing, get it out of there. So what's the whole point of this? Well, the whole point of this is these are going to be used down the road. Now watch what happens as I am zooming in around this point. Okay, so I'm going to zoom in. And I'm going to continue to zoom in closer. And what's happening? I'm going to zoom in closer. My tangent line and my curve virtually become the exact same thing. So what I am doing here by writing this tangent line, I am linearizing my graph at x equals 1. And we're going to use that graph down the road to make approximations for y values on rather complicated functions. Okay? Well, because you haven't done many of these, come on, baby, give it back to me. We're going to do one more problem, okay? We're going to do one more. This is not in your note sheet. After this problem, I'm quitting, and I'm going to finish the note sheet tomorrow, and then Your review day is going to be Friday and our test is going to be moved to Monday. But we're going to do another example here. This is not in your note sheet again. Hit pause, grab a sheet of paper, give it a shot so you can follow along. So what we're going to do is we're going to find the equation of a line tangent to f of x. I have a brand new function and it's going to be at x equals 3 this time. Okay. First and foremost, we need a point. Well, the point on the graph at x equals 3, that is whatever f of 3 is going to equal. And when I plug that in, I have 2 times 3 squared minus 3 times 2. I get 9, I get 18. Oh, 2, that's a 3, sorry. 18 minus 9. So f of 3 equals 9. It's simply a crafty way to write an ordered pair this way. It's really 3, 9, okay? My slope. I'm going to find the exact slope. I'm not going to approximate it because I know you guys are going to need practice with this. So what we're going to do to approximate this, we're going to find the AROC, okay, from 3 to 3 plus h. That is what we're going to do. And we're going to do that by using a limit. So we're going to say the limit as h approaches 0 of f of 3 plus h minus f of 3 all divided by 3 plus h minus 3. And you remember how I said that whole thing's going to go out of there. Notice my 3 here and this 3 cancel. So at this point we can stop because we know these 2 points up here, whenever I'm subtracting them, I'm only going to be left with an h, okay? And what I'm going to do is now I have to find out what is f of 3 plus h. So that's going to be a limit as h goes to 0. And again, I'm making my parentheses here. This guy is a big problem that everybody forgets to distribute into that set of parentheses in the end. But what is f of 3 plus h? Well, it's 2. There's an h, or an x, I'm sorry, so I have to plug a 3 plus h in for it. That first one squared, minus, there's a 3, oh, there's another x, so I have to put in a 3 plus h, minus f of 3, well, that's just plugging 2 times 3 squared minus 3 times 3. Okay? And all I'm going to do is I'm going to keep plugging and chugging along here. Come on, baby. Get it up a little higher. And what I'm going to do is I always expand this guy up here. So that's really 9 plus 2 times 3 times h is 6h plus h squared. Now I got to distribute my 2 to it, so that's going to be a limit as h goes to 0. That's going to give me what? 18 minus 12h plus 2h squared. Now I got to distribute that, minus 9 minus 3h minus. Now we already found what f of 3 is over here, didn't we? We know that that's going to turn out to be a 9, so I'm going to skip that math and I'm going to put a 9 there, and I'm going to say it's over h. Check it out. 9, negative 18, positive 18. And the only thing that's allowed to be in the numerator after you make your cancellations are terms with h. So really, I have the limit as h approaches 0 of, this is a plus here, sorry, because that was a plus there. So 12 minus 3, I get 9h plus 2h squared over h. So that's really the limit as h goes to 0, because if I try to take my limit right now, I'm 0 over 0, so I got to factor that h out. There goes my 0 over 0. I can evaluate my limit, and it is going to equal 9. What does that mean? That means f prime of 3 equals 9. In calculus, that means m equals 9 at x equals 3. Okay, that's what we know. So I've got my slope and I've got my point, and now I'm just going to plug it in and say y minus y1 equals m times x minus x1. And I am donezo on that one. All right. I'm going to finish this up tomorrow, and that's it for today. Hopefully it won't be as long tomorrow. Have a good rest of your day.